So guys, welcome you all to this video. This is Infinite Series part 3, and here we will start this concept from where we left in the last video, that is necessary condition for a series to be convergent. For a series, that is summation an, to be convergent is take the limit of this nth term and it will be equals to 0. So this is necessary condition for a series to be convergent. It is not sufficient condition. Why? We have some counter example for that, and we will discuss this counter example with you, but I expect that you will go to any standard book and study few more examples for your own satisfaction. But for the proof of this necessary part, obviously the idea is something like that. This an, you can write this by s minus s n minus 1, because you know that Sn means a1 plus a2 plus it is going on to an minus 1 plus an, correct? So up to an minus 1th term you have this Sn minus 1 plus an. So immediately what you can write, your an equals to Sn minus 1. There is nothing special. Now take the limit both side. Limit as n tends to infinity, obviously you have limit of Sn tends to infinity minus limit of Sn minus 1 n tends to infinity. So this series, it is convergent, so it will have a finite sum, and say that sum it is s. Okay, so Sn tending to that sum, it is s. So what you have as n tends to infinity, s minus s, so it is equals to 0. Correct? This is more or less the idea behind the proof of this necessary part. Okay, but for the sufficientness, you have example, very standard example. It is summation 1 by n, the harmonic series. This is harmonic series, and you know this series, it is divergent. Obviously we have plenty of technique or tests by which we can show this series it is divergent, and we will come with the subsequent videos regarding the tests and all these things. Okay, so for that you have to wait a little bit, but we can show that in this particular discussion the sufficient part it is not holding on, because limit of this an, it is nothing but limit of this 1 by n, and it is equals to 0. So it is equals to 0 in this case, but this series it is not convergent, so it is divergent in fact. So whenever you have for a series limit of this an equals to 0, you cannot claim about the convergency. For that convergency part you have to test, but in contrapositive way, if you have limit of that nth term not equals to 0, immediately what you can conclude is that the series is not convergent. That's for sure. All right, so this is the advantage of this necessary condition, because it works very usefully in contrapositive way. Fine. Now we are moving on to another very important and handy necessary condition. It is sometimes known as Abel's theorem regarding series chapter, because there are a number of theorems, namely Abel's theorem. So this necessary condition, it says that first of all you need to have this sequence an as monotonic decreasing. Okay, it is the first criteria for this Abel's theorem, and it says that for this series an of positive terms, the necessary condition for an, this series, to be convergent is is what? Is take the limit multiplied with n into an. This limit, it should be equal with 0. So this is necessary condition. But take care of these two terms. That is, first of all, sequence an should be monotonic decreasing, and this series should be the series of positive terms. Correct? It is again a necessary condition. So for that part, I'd like to give you one counter example here, that take the series an as 1 by an plus b. A multiplied with n into b, where a and b, these are greater than 0. Alright, so in this case, what you have, an equals to 1 by an plus b, and your duty will be to verify whether an is monotonic decreasing or not. But I am giving you that this an, sequence an, it is monotonic decreasing. Correct? And also, as a and b are greater than 0, so it is series of positive terms. Now verify whether this one holding or not. N into an, take the limit, you will find that 1 by a you are getting. Correct? 1 by a you are getting, so it is not equals to 0. So immediately what you can conclude about this series, it is not a convergent series. In fact, as it is positive term series, so it must be divergent series. Correct? So this is, you can say, another very useful necessary condition regarding this chapter of series, and these are all very preliminary thing. Now we are moving on to some assignment related or questions what I want to give you, because in the last video we came across very famous Cauchy's principle, and these are all applications of Cauchy's principle. Okay, so take it as your homework and let me know in the comment section whether you are comfortable with all these things or not. Otherwise I will give you some PDF or related video of PDF. Okay, so the first thing is that check whether 1 by n is convergent or divergent by using Cauchy's principle. Second one, the harmonic series, it is divergent, verify. These are check. And the third one, 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus so on, whether it is convergent or divergent, check. Obviously all these things can be done by using various kind of tests. All these tests we will discuss in our subsequent videos, but up to today's video or lesson, I want you that you should be comfortable with the things whatever are basic regarding this chapter of series. And as the series or as the lecture series goes on, you will find that various tests will be there which will be very much helpful for you. But before that, you must be clear with the basics. That's why I'm just giving you as your homework. Try it. At least you should try it. Okay, fine. Now up to that we have one part, that is up to Cauchy's principle. Now with basic understanding of some general theorems, we will be moving on to the tests regarding series of positive terms. So some general theorems. Let n be fixed positive integer. First of all, we fixed positive integer. Correct? Then if this series we take as ak, k runs from 1 to infinity. Alright, this series and this series where k runs from n plus 1 to infinity. So we truncate up to first n term, then the remaining series this one and the initial series this one behave alike. That is, they are both convergent or divergent. If the first one converges, then the second one is also convergent, vice versa. Okay. Second general theorem, it says that suppose your series k runs from 1 to infinity, it converges to S. Then what you have, ak where k runs from n plus 1 to infinity, this converges to S minus first n term, a2 to an. Yeah. So the moral of the story is that you just eliminate finite number of terms, the nature will be same for the both of these series. Okay, but if the first series converges to a particular number S, then the second series will converge like this way, S minus up to that finite number of terms. Okay, these are two very basic general theorems, and also there is another one that says that if you have, suppose lambda greater than 0 a constant, okay, then if you have a mother series like this way, this one and some lambda multiplied with k, ak, that is k runs from 1 to infinity, these two series behave alike. That is, if the first series converges, then the second one also converges, and if the first one diverges, then the second one also diverges. Okay. That means in generalized statement it says that the multiplication of each term of that series by a non-zero constant doesn't affect the behavior of the series. Alright, so these are some general theorem. With all this basic understanding, now we are in a position to start the series of positive terms, where we will find many, you can say, tests are there, especially test will be there, and some question we will tackle. Okay, so fine, meet you soon in the next video with plenty of tests with their example as well. Wait till that moment and meet you soon in the next video. Till then, stay safe and stay your home.